Good evening, ladies and gentlemen. My name is David Netto, and physics is my business. And today, I'm going to talk about something that might seem more like science fiction, and that is time travel. So it's a very popular subject. Many movies, films, comics, books, the whole gamut. Everyone loves time travel. And it might just seem like that, just like fiction. But actually, time travel itself does have some science fact, and that's hopefully what we'll talk about today. So, a little bit of background. There we go. Around the turn of the century, Einstein comes up with his theory of general relativity, and the Reader's Digest version of this basically says gravitational fields, gravity, affects time and space. So it warps time and space. So, for example, the Earth we're living on, in the 1950s and 60s, the United States Air Force did an experiment. They took the best atomic clocks they had, they synchronized them on the ground, they put one in a plane, flew it around the globe, the other one they left back at base. When they brought the two clocks back together, the clock that was up in the air ran fast. So what happens is gravity warps space, and it causes clocks in weaker gravitational fields to appear to run fast. And this effect is proportional to the strength of the gravitational field. So, what objects in the universe have really strong gravitational fields? One such object is a black hole. So stars that are much more massive than our sun can potentially, at the end of their life, when they're done burning their nuclear fuel, they can collapse under their own weight. And they form what we call a black hole. Black because its gravitational field is so strong, not even light can escape it. So if you were to hop in your spaceship, put yourself in orbit around a black hole, let's say maybe for an hour. So to you, in your ship, an hour passes kind of boring. But when you leave the black hole, radio back to base, they tell you, you've been away for 6 years. This is that gravitational field that is warping space. And because the black hole has such a strong gravitational field, that effect is huge. So in essence, you have time traveled. It's kind of the boring, not very sexy forward time traveling. I mean, that's what we're doing right now. But one might ask, what about traveling backwards in time? So relativity, the equations of relativity allow backwards time travel. They allow it in the sense that there are mathematical solutions that allow you to travel backwards in time. And they're just that. They're just mathematical solutions. They're not necessarily physical or real. One of the reasons why you would be inclined to believe they're not real is the problems that come up with causality, or cause and effect. So we like to encompass this in a paradox called the grandfather's paradox. And the basic idea is, if you go back in time and kill your grandfather, well, your grandfather doesn't give birth, well, he doesn't give birth to your father, but your father doesn't get born, you don't get born, so you can't go back in time to kill your grandfather. So we have this disturbing cause and effect relationship. So this would sort of seem to say, backwards time travel doesn't work. Now, general relativity, as I said, allows it, but the other laws of physics are a little bit sketchy. So in the 1960s, Stephen Hawking, working in black holes, he combines general relativity, some quantum mechanics, some thermodynamics, and what he finds is that there's this sort of what he calls a chronological protection agency. There's sort of like this auspicious outside agent in the universe that says you can't do time travel. It just doesn't work. So the thing is, it's not a definite no. It's sort of like a maybe no. In order to get a definite answer, you actually have to come up with sort of a complete quantum gravitational theory, which we actually don't have. And physicists have been working on this for many, many years, and so we're still working on it. So we kind of can't say definitively you can travel backwards in time, but let's say we go back to our friend the black hole and maybe do something a little bit else. So around the 1980s, another physicist, Leonard Susskind, also doing some work in black holes. Now, there was a problem with black holes. As I said, the gravitational field's really, really strong. Light can't escape it. So if something goes into the black hole, it's never going to come out. Now, this is a bit of a problem because it's sort of like destroying information in the universe. It's information that goes somewhere that we can never get out. And this was a big problem. And Dr. Susskind came up with the solution that essentially, when things go in a black hole, the information of what goes in the black hole sort of gets smeared on the outside of the black hole. And so what you can do is you can think of a black hole as sort of this quantum DVR. Everything the black hole sees, that light goes into the black hole, information gets smeared on the outside. So if you wanted to just be an observational time traveler, nothing wrong with that, doesn't hurt causality because you're not affecting anything, you're just looking at things. So you can simply scan the surface of this black hole, and you can travel back in time and see anything you want to see, from the birth of the universe, anything planet Earth, anything you want to see, it's there on the black hole. So, unfortunately, how you actually go about constructing the device to let you read a black hole, sort of leave that to the experimentalists to figure out. But it's an interesting idea nonetheless, that time travel sort of, in some manner, is not exactly science fiction, but a little bit science fact. Thank you.